And it only seems like my 5th lecture to you. It's really only my 3rd. So what I'm going to do today is sort of finish up the discussion of deformation spaces and hyperbolic 3 manifolds. We sort of started at the end of the first talk, and then we'll have a brief interlude to prove Thurston's tameness theorem, just because it came up twice yesterday, and it's a really cool argument, and a really quick one. And then maybe I'll talk a little bit about dynamics on characterized, just so we can have something in the mini-course that happened in the last 5 years. So, remember our setup was that we have a compact, orientable, atoroidal 3 manifold. So that those topological, irreducible should be there too. Those topological assumptions are just exactly the topological assumptions you need for the interior movement of a hyperbolic structure. And throughout the talk, we're going to assume the boundary doesn't have any toroidal components, not because anything really goes wrong, but because everything is more technical to say, and it's going to make it easier to talk about. So, the deformation space we think about here usually, just an interior is a complete hyperbolic structure. Yeah, just a complete one. Right. We're talking about the space of discrete faithful representations of pi1 of m into PSL2C. So what is a discrete faithful representation? Well, it's really another way of saying a marked hyperbolic 3 manifold. So you can think of this as just like Teichmüller space. The elements of Teichmüller space are marked hyperbolic surfaces, and if you want, you can think of them as representations in the PSL2R. So when you have this representation, its image is the discrete subgroup of PSL2C, which you can think of as the orientation-preserving isometries of H3. You quotient H3 out by that, you get a hyperbolic 3 manifold, and the fundamental group of that hyperbolic 3 manifold is identified by rho with a fundamental group of M, so you get a homotopy equivalence. So starting with the representation, you get this pair, which is a hyperbolic 3 manifold and a homotopy equivalence. Down here, if you want to put a topology on this space, it naturally sits within what's called the character variety, which is essentially discrete faithful representations up to conjugacy. Okay. And if you start in the other direction, if I have a marked hyperbolic 3 manifold, which is some hyperbolic 3 manifold and a homotopy equivalence from M to that hyperbolic 3 manifold, that hyperbolic 3 manifold is the quotient of H3 by some subgroup of PSL2C. And so if you take H star from pi1m to pi1n, you can think of that as a representation from pi1 of m into PSL2C. So you could go back from a marked hyperbolic 3 manifold to a representation. Okay, well, we spent a lot of time talking about on Tuesday our 2 results of Marden and Sullivan. One, that convex co-compact representations are quasiconformally stable, meaning if you wiggle them a little bit, they stay quasiconformally conjugate. And also that if you have something which is structurally stable, which means all the representation nearby are injective, then you must have started with something convex co-compact. So if you put those 2 together, it says that the interior of this space consists exactly of the convex co-compact representations. Because if you're in the interior, when you wiggle it, you stay inside, which means you're structurally stable, which means you're convex co-compact. Okay. And we saw in Ken's talk this morning that if that in fact the space is the closure of its interior, or that another way of saying that is that every discrete faithful representation is a limit of convex co-compact representations. Okay? Now, associated to a convex co-compact representation is a piece of topological data, well, which is essentially a homeomorphism type, but remember, a representation that gives this homeomorphism type of marking. So we think of it as a marked compact 3 manifold, where the compact 3 manifold is just this conformal mortification, which we were calling n rho f. And then the homotopy equivalence comes from the representation. And then you can define what you can think of as sort of as a topological titular space of marked compact three manifolds up to homeomorphism. So basically your elements are, I wrote it up there, but you need the diagram. So if you have an element is a homotopy equivalence from M to M prime, and the equivalence relation is exactly, if you have M here, and you have M1, H1, H2, M2, if you can fill this in with an orientation-preserving homeomorphism that's in the right homotopy class. So J is homotopy equivalent to, I guess we can't use the word inverse here, so we have to do J compose H1 is homotopy equivalent to H2. So that's just like the definition of titular space, except these are topological objects, so the word isometry doesn't make any sense. We replace it with the obvious thing in this category, which is homeomorphism. And then you get a map from the interior of H of M into the marked homeomorphism type, which we forget the geometry, and all we do is remember the topology. Okay? So Thurston's hyperbolization from this viewpoint just says that this map is a surjection, which means that every marked homeomorphism type arises, and moreover, that not only can you make a hyperbolic structure on any three manifold of the right type, you can also make a convex co-compact hyperbolic structure. Okay? So the one ingredient which is sort of missing to complete the whole picture, to understand the interior of H of M, is we've got to understand what the components look like. Okay? And it's going to turn out that the components are exactly in one-to-one correspondence with these marked homeomorphism types. So I think I maybe said this in words, but we're going to lay it out a little more carefully. We get a picture of the interior where each component is determined by a piece of topological data, which is the marked homeomorphism type, and then each component is then parameterized by analytic data, which comes from the conformal boundary. So the missing ingredient to really say that is something known as Marden's isomorphism theory. And he said that if you have two convex co-compact hyperbolic three manifolds which are homeomorphic, then they're quasiconformally conjugate. So in this sort of formal language, it says if you have two representations and they have the same marked homeomorphism type, if and only if they're quasiconformally conjugate. So sort of we have really all the ideas to go back and forth. First of all, if you have a quasiconformal conjugacy between two Kleinian groups, well, that quasiconformal conjugacy can be extended to a bi-Lipschitz conjugacy between the group actions on H3. And hence, if you take that bi-Lipschitz conjugacy on H3, it descends to a homeomorphism between the quotient hyperbolic three manifolds. Okay, so that's one direction. Marden actually showed what was known at the time as the quasiconformal maps on the boundary extend naturally to quasiconformal maps on the interior. We didn't use bi-Lipschitz. On the other hand, if you have two manifolds and all you know is that they're homeomorphic and they're convex co-compact, well, remember that we saw that off of some convex set, which was the convex core, they have this very specific metric. Up to by Lipschitz constant, they're cosh squared t ds squared plus dt squared. They have this very explicit metric. We totally understand it. And then we just take one end and we move it over to the other using these explicit coordinates, and you just check that's by Lipschitz. So if you can just fix up this homeomorphism to be a bi-Lipschitz homeomorphism from between the hyperbolic three manifolds, you lift that bi-Lipschitz homeomorphism to a bi-Lipschitz homeomorphism on H3, conjugating one Kleinian group to another Kleinian group, and then a bi-Lipschitz homeomorphism extends to a quasi-conformal homeomorphism. Some weird feedback? Maybe I'm just hearing it. And this quasi-conformal homeomorphism conjugates the group action on the Riemann sphere to the group action on the Riemann sphere. So it gives a quasi-conformal conjugation of the representations. Okay. So now you know that, in fact, the components of the interior are just in one-to-one correspondence with the marked homeomorphism types. Because if two things have the same marked homeomorphism type, they're quasi-conformally conjugate, and we saw that quasi-conformal deformation spaces are connected manifolds. And moreover, we saw that if you have, excuse me? We fixed the manifold. So that fixes the group, yeah.
Oh, marked homeomorphism.
Yeah, marked homeomorphism type, yeah.
So if we fix the group, how many homeomorphism types?
There could be infinitely many. I'll give you an example. I'll give you an example where there's finitely many in a minute. You want to see an example there's infinitely many just for fun?
Yeah, yeah.
Okay.
I mean, I like to just fix the group, and then make it like the manifold set.
Right, so, sort of some groups have only one homeomorphism type, some groups have finitely many homeomorphism types, some groups have infinitely many homeomorphism types. So, marked homeomorphism types, yeah. Actually, they all have only finitely many homeomorphism types. I need the word marked there. So what do you need to have infinitely many marked homeomorphism types? It's really the same thing as having infinitely many really different homotopy equivalences, which are not homotopic homeomorphisms. So here's a construction of infinitely many. Take any old manifold, complicated manifold, and then add a one handle to it. And I'm going to take the same guy over here. I'm going to add a one handle to it. And my homotopy equivalence is going to be the identity off the one handle. And I'm going to just take the one handle here. And it's going to go all around the inside and go messing around and come back over. And typically, there's going to be infinitely many ways to do that. Okay, and they're not homotopic to homeomorphisms because you think about this curve, which now is homotopic to the boundary. Its image is no longer homotopic to the boundary. Therefore, this homotopy equivalence can't be homotopic to homeomorphism because it can't take the boundary to the boundary. Okay, so once you have a handle, typically, you get infinitely many marked homeomorphism types. Okay, so what I was saying here is if you have theta of rho is some marked homeomorphism type m prime, what we saw was that the quasiconformal conjugates, the set of representations quasiconformally conjugate to rho was exactly the Teichmuller space of the conformal boundary. Perhaps modded out by something. And this is just the Teichmuller space of the boundary of m prime, modded out by something. So if you assume pi 1m is freely decomposable, then you get one Teichmuller space, one copy of Teichmuller space for every marked homeomorphism type. Okay, I'm going to have 2 or 3 examples in a minute. So that means the fundamental group doesn't split as a free product. And if you're a topologist, what it means is if you have a curve in the boundary, then the can't be is not homotopically trivial in the boundary. It's not homotopically trivial in the 3 manifold. We say incompressible boundary. We can't take the boundary to lie.
Is that example there as well, right?
No, that's compressible boundary. That would be on the next slide. So it's nice in this case. If it's freely decomposable, you just get Teichmuller spaces.
Oh, I see.
Basically because the marking of the 3 manifold group determines the marking of the boundary. But for instance, on a handle body, if I mark the free group, there's many different ways to mark the boundary of the 3 manifold, which is a surface which is consistent with that. Okay, so in this freely decomposable case, life is good. There's only finitely many marked homeomorphism types. Each associated component is just a Teichmuller space, so it's a ball. So the interior is a finite union of balls. So that's good. That's the good case. And then the slightly less good case is where it's like this, where you had compressible boundary. Well, then if each component is the Teichmuller space of the boundary modded out by this what's called the twist group, which is the group generated by Dane twists about curves in the boundary which can be compressed in the three-manifold. So the bad news is that typically there's infinitely many homeomorphism types. That's just the reason there. And typically this group is infinitely generated. That's due to Darren McCullough. But still you have this fairly nice picture that you have this enumeration, and you have these components. Each component is a manifold, enumerated by analytic data. It's not so bad.
I mean, that's a discrete group action, right? So
Right. So this is identified with a subgroup of the mapping class group of the associated type in their space. So the action is properly is continuous. Moreover, it's a torsion-free subgroup. So the quotient is not an orbifold, it's a manifold. So it's pretty nice. Okay, so what's some examples? Well, the simplest example, the one that you're probably most used to hearing people talk about, is just the surface cross I. And in that case, there's only one marked homeomorphism type. Because if I give you a homotopy equivalence from the surface cross I to some other three-manifold, it's always homotopic to an orientation-preserving homeomorphism. There's a special thing, which is that if you end up finding an orientation-reversing homeomorphism, you can just flip the two boundary components. There's something very special about a surface cross I. The other very simple case is that if M is acylindrical, meaning there's no essential annuli, meaning if there's any annulus in your three-manifold, and the core curve of the annulus pi1 injects, then you can push it into the boundary. Okay, and in that case, every homotopy equivalence is homotopic to a homeomorphism, maybe not to an orientation-preserving one. So you get two marked homeomorphism types, and it really just keeps track of the orientation. So you get two components of AH of M, the type meter space of the boundary, and the type meter space of the complex conjugate of the boundary. Now notice this, for instance, this is also true for a closed three-manifold. For a closed three-manifold, there's the representation associated closed three-manifold, and there's its complex conjugate representation. So you get 2 points in the closed case. This is sort of what Moscow rigidity tells you. Okay, so now let me draw you a case with incompressible boundary. And this is the picture I was drawing rather quickly at the end of the first talk, but I'm going to go into a little more detail because it's a quite well-studied example where we have n-1 factorial components. So basically what I do is I take a tin can, or an annulus if you prefer, and n slots in this annulus. In the first slot, I take something of genus 1. In the second slot, I stick in a disk with 2 1 handles, and all the way down to the nth slot, where I stick in n 1 handles. So we might denote it something like 1, 2, n. That's a 2 complex xn, and then you're going to let my manifold is just going to be a regular neighborhood of xn. I embed that picture in R3, and I just take a little neighborhood of it. How do I get, what's a recipe for constructing things which are homotopy equivalent to it? I just take any old permutation. So if I take any element of the permutation group, then I can make the exact same picture. And so I stick tau of n on that disk, and then tau of 1 up here. This disk gets tau of 2, and then m tau n is a regular neighborhood of x tau n. So that's x tau n. Now there's one obvious homeomorphism in this picture, which is if I picked up the first, if I sort of dropped the first disk and then shoved it and then stuck around and stuck it on the bottom, that would be result in something homeomorphism. So if I cyclically permute, that doesn't change the homeomorphism type.
I don't see that.
Think of the tin can as a conveyor belt. And you're going, and then the one on the top sort of goes all the way around and comes back up on the bottom.
You're picking it up, so you got this outer boundary.
Yeah, so what this is when I thicken up, here's what I think. If you have an annulus, when you thicken it up, you get a solid torus. And when you thicken up each of these disks with handles attached, you get an I bundle. and you get an I bundle attached along a bunch of parallel annuli, and you just rotate the annuli around. That's all you're doing. Yeah.
It helps to eat these in turkey.
Yeah. Don't get smart or squash you like a fly. Anyway, so it turns out that's the only issue, and you can prove it's sort of, you know, an exercise in the characteristic submanifold theory to show that this is just sigma n modded out by the cyclic subgroup. So you get a set of cosets, n minus 1 factorial cosets, and these are the marked homeomorphism types. But, yeah, so it's characteristic submanifold theory to see that. Okay? We're going to come back to this example in just a minute. So now we're going to talk about Bumpanomics. So the first thing that happened in Bumpanomics was that we saw that any two components of the interior of H of Mn, where Mn's that manifold, bump. So we think, so why is that surprising? So you have these, if you look at the, maybe I should draw them dotted. You have here's the interior of H of Mn. There's n minus 1 factorial of these components. Now why do you not think they bump? And why might you say, you know, spend 2 years of your life trying to prove they don't bump? Well, it's because everything here has one homeomorphism type, and everything here has another homeomorphism type. So if they were to sort of look at their closures, and they were to bump like that, there's this point rho here, and what should the homeomorphism type be? Well, if you come from this side, you have one homeomorphism type, so we should have this, the homeomorphism type of this guy. If you come from the other side, you should have the other homeomorphism type. So there's two different predictions for what his homeomorphism type is, therefore that point can't exist. Well, but unfortunately it can't, or fortunately actually, it can. It turns...
That's still injected.
Yeah. So every limited discrete faithful representation is discrete faithful. So that's still, yeah, in fact, it can have this, so this point can occur so that it has this homeomorphism type, it has this homeomorphism type, or it has some third entirely different homeomorphism type. So you can't predict what the homeomorphism type of that thing is at all, it turns out. And it turns out that any two of these components can bump. And in fact, I don't have it on the screen, but John Holt showed that there's a point which is in the closure of all n minus 1 factorial components. They all bump at a single point. I can't really draw that picture, but they do. And I'm going to sketch the proof of it for you in a minute. But of what? It can be anything you want. It can be any of the n minus 1 factorial components. They, in fact, intersect at a point with any of those different homeomorphism types. Yeah. So it turns out that homeomorphism type can do...
You're still the same finite family homeomorphism.
In this particular thing. So now, what I'm not really going to... I'm just going to give you the sketch of the construction in this case. But, in fact, we got a real topologist on board, Darryl McCullough, and that allowed us to sort of characterize exactly what homeomorphism types changes can occur. And it turns out that if two components bump, well, how do these, I don't want to say words, but how do these two differ? Where you have a solid torus component, and you remove the solid torus, and then you rearrange the way stuff is glued to the solid torus, and you glue it back, and then you get a new manifold, and it's homotopy equivalent to the old manifold. And it turns out, if you have a change of homeomorphism type, which is like that, and the other thing, the word primitive there occurs because notice that these I bundles are glued to the torus along longitudinal annuli which only go once around the core curve. So it turns out that anytime you have a homomorphism type, a change of homomorphism type like that, those two components bump. And if the two homeomorphism types don't differ by what we call a primitive shuffle, then those components don't bump. so you can get a complete analysis.
Can you give a little more concrete example on this?
I'll give you an example. How about an example where they don't bump?
I mean, an example of this operation you just described.
Okay, so let's think about, what do I want to erase? This one. So what's another way to think about this? What we just, this manifold we made. So on Mn, we take a solid torus, and on its boundary, we have a bunch of annuli. There's annulus 1. So there's A1, there's A2, there might be n of those. And to A1, I glue punctured torus cross I. Right? And I glue it by gluing the puncture across I as an annulus. So I glue that annulus to annulus 1. And to annulus 2, I take a punctured surface of genus 2 cross I.
Cut a little disc out.
What?
A puncture you can hold.
Yeah, I mean, one hold would be a better word. That's a good point. One hold.
You were picturing a puncture, right?
Yeah, that's true. One hold torus cross I, one hold surface of genus 2 cross I, and what we did to make the new one is we just, maybe I glued the one hold torus cross I to the second annulus, the two hold torus, and the one hold surface of genus 2 cross I to the first, and the one hold surface of genus 18 to the fifth, and I just rearrange. So that you're allowed to do. Okay? And anything else you want. So for example, I might...
Just re-describe these manifolds.
Yeah, this is the exact same manifold. But in general, you might do anything. Suppose I take a torus with a bunch of annuli in it, and I pick 18 different acylindrical manifolds, and I glue them to that in some order. Then I could rearrange the order in which they're glued, and that operation is called a primitive shuffle homotopy equivalence. And maybe I have more than one torus. Maybe I have a handful of torus, and I do this rearrangement on each of them. But here's what you can't do that looks very similar. So suppose I took a solid torus, and instead of taking an annulus that goes once around the boundary, I can make an annulus go twice around the boundary. So that's annulus 1, and I can take a bunch of parallel copies of that. And now I can glue my I bundles to those annuli. And again, I get n minus 1 factorial homeomorphism types. The exact same thing, but all those components, none of those components bump. Because I'm only allowed to do the rearrangement when the gluing is along one of these longitudinal annuli. Yeah, that's a solid torus again. But now, so if it were a not solid torus, like, what's the difference?
How do you identify the longitude?
Yeah. What's the core curve? I mean, so something's longitude.
That's also the core curve.
Oh no, that's twice the core curve.
That's twice.
Yeah. Well, yeah, so I can't, like longitudinal, like if I Dane twist about a meridian, that's still a longitudinal annulus.
Right.
Yeah,
You're
right.
going around once.
Going around once. Yeah, I shouldn't use picked, yeah.
Okay.
Should just say what I mean instead of using words. Okay, go around once. So if you do the same thing, you go around twice instead of once, you can't have any bumping. So you have n minus 1 factorial components, none of them bump.
So when you shoot the bumping, you actually understand that in some cases the homeomorphic type, or you just say that there exists a bumping?
Well, we construct the bumping point. So because we explicitly construct the bumping point, we know the homeomorphism type of the bumping point. I'll show you the construction. When you see the construction, you'll see it's very concrete construction. And there really ought to be all sorts of things going on causing bumping, but we really only understand this one construction. Okay, so what does the bumping construction do? So this just needs, we just need we need pictures, because those words are hopefully just going to guide the pictures. The words themselves probably aren't going to help you that much. So I'm going to use a schematic for this guy. So this guy I'm going to denote 1, 2, 3, 4. And that's supposed to mean, so this vertical line is the annulus, and this is the one spot. This is the disk with one handle. This is the disk with two handles. So what I want to do is I want to thicken it up, and I'm going to remove the core curve of the solid torus. So I'm going to make a manifold Mn hat equals Mn minus the core curve of solid torus. So my schematic for that is going to be this. Where I label them 1, 2, 3, 4. Okay, that's my schematic. I've removed the core curve, and now instead of having a solid torus, I have this thickened torus. So imagine taking this picture and rotating it around in a circle. And I can then pick another thing. So this is a different homeomorphism type. It's the one where I do, instead of 1, 2, 3, 4, 1, 3, 2, 4. That gives a different homeomorphism type. And I'm going to take an immersion of this guy into here. So I immerse, one goes around, then actually I want to go this way. So 1, 3, 2, 4. So this is an immersion. Did I call it H on the slide? Yeah, good. So that's my immersion. Okay? And what's a key property of my immersion? If I take the cover, so key topological fact, is that the cover of Mn hat associated to H star of pi 1 of m tau n is homeomorphic to m tau n. So I have an immersion of this guy in, I look at the image of the fundamental group, I lift the cover, and it has the right homeomorphism type. Why should you believe that? Well, there's an unraveling of this cover, which goes, there's a cyclic cover of this guy, which goes 1, 2, 3, 4, 1, 2, 3, 4. And that's sort of an intermediate cover. And what does this guy lift to? This lifts to 1, 3, 2, 4. So it lifts to an embedding in that cover. And that's the reason why when you pass to the full cover associated to the subgroup, it has the right homeomorphism type. Okay, well now, if you have a manifold with a toroidal boundary, you can stick a hyperbolic structure on it. And
sort of convinced me, but it looks like there's going to be more rings coming off when it goes into the cover.
yeah, this is going to be, what I've built is a compact core for the cover. And every manifold which is topologically tame is homeomorphic to its compact core. If I really wanted to be careful, that would be a proof. Yeah, but this is why. Okay, so now if you have a manifold, hyperbolic, if you have a manifold with toroidal boundary, you can hyperbolize it and have a rank 2 cusp, assuming it, you don't fail some of the basic topological obstructions. And so then you can do Dane surgery, which means you take that torus and you glue a solid torus to it, and I'm going to glue it along the 1I meridional curve. And one topological fact is here, when I glue it along the 1I meridional curve, it's homeomorphic. That's the same thing as gluing along the 1, 0 curve up the homeomorphism. So you got a little topological fact to check. Maybe I don't want to go into that too much. So what I do now, what Thurston tells me, if I have a sequence of Dane fillings with coefficients going to infinity, like 1i, I can get a sequence of hyperbolic three-manifolds geometrizing those Dane fillings, and they converge to the limit manifold. Okay? So what do I have? I have an immersion of this guy into this guy. Well, then now I take it into the hyperbolic manifold, and the hyperbolic manifold, and this hyperbolic manifold is very close to its Dane-filled manifold. Okay. So, one way of saying that is that there's a natural inclusion of the manifold into its Dane filling, right? You just map the manifold minus the solid torus into the manifold with the solid torus added. I call that R sub I, and so now I can define representations. I take the ith representation, so I take H, this immerses this into here, and then I Dane fill it, and then I map it into the Dane filled manifold, and I take the deduced map on phi 1. And it turns out that if you look at this immersion, this is going to be a homotopy equivalence into the Dane-filled manifold. And the Dane-filled manifold has exactly homeomorphism, the interior of just the original Mn. But it converges to the limit, and the limit representation is just H star, because the Ri stars are converging to the identity. So your limit manifold all of a sudden now has a different homeomorphism type. I'm not sensing a lot of belief. What? I produced a sequence of hyperbolic three-manifolds where all the elements in the sequence have the homeomorphism type, the interior of the original manifold Mn, and the limit has a different homeomorphism type. And then I also would have to show that I can approximate something with homeomorphism type, the interior of the new one, by what you expect. But that's easy to do. You do the same trick. The geometric limit is this drilled out manifold. So the algebraic limit.
So the geometric limit has missing symmetric curve.
Yeah. So the geometric limit is this curve, is this manifold with the core drilled out. But if you take the associated algebraic limit, it's the subgroup associated to the immersion. Yeah. So I mean, this is. This is sort of like similar to the trick Kerckhoff and Thurston used to show that discontinuity of the mapping class group of the boundary pair slices or something like. Anyway, let's let me not go off too much of a tangent. So it's just a little. Basically, there's a few little topological tricks, and then there's Thurston's hyperbolic Dane surgery here. Okay, and then this is sort of moving up to intermediate Bumpanomics. This is components bumping. Then it turns out that even in a case like quasi-Fuchsian space, you can have something called self-bumping, which means there's some point which looks like that if you look at it, any small enough neighborhood of the point, it disconnects the interior. So Kurt used this construction to show that quasi-Fuchsian space self-bumps. And then Ken Bromberg and John Holt came in and showed that whenever you have a primitive essential annulus, which means you have one of these essential annuli, the core curve injects, and if you look at the image of the core curve, it generates a maximal abelian subgroup, meaning it isn't sitting inside the Z plus Z subgroup, and it doesn't have any roots in the three-manifold group. Whenever you have a primitive essential annulus, every component of the interior does this self-bumping thing. Okay, and so this was, I mean, it could look like it's just sort of a direct generalization, but Kurt's proof relies very heavily on understanding the space projective structure, so they really had to do some new stuff to get this. It's not just a simple generalization, which could be how it looks here. And then most recently, in the last few years, Ken Bromberg and then Aaron Magid showed that if you look at this space of hyperbolic three-manifolds homotopy equivalent to a closed surface, it isn't even locally connected. Okay, so you know, and this is conjectural Bumpanomics. So we only know, the only tool sort of we have to produce this sort of nasty bumping and self-bumping phenomena revolves around this trick. When I did this trick, you know, you can generalize it by thinking whenever you have an essential annulus, you remove the core curve of the essential annulus and you do this trick. So at the moment, that's sort of the only trick we got. But if you sort of look at the pictures and think about it, Ken has a sort of persuasive heuristic that even when there aren't essential annuli, you should still have lots of self-bumping, and in fact your space should not be locally connected. But right, there's very little evidence of that in terms of actual proof. So I thought of one way one could attempt to measure the fact that complex dynamics is more complicated than Kleinian groups would be to look at one-dimensional deformation spaces and look at their boundary and look at the competing Hausdorff dimensions. So there's, Misha mentioned at the end of his talk, that the boundary of the Mandelbrot set has Hausdorff dimension 2. So this is the most natural one-dimensional deformation space in complex dynamics. The most natural one-dimensional deformation space in Kleinian groups is the boundary of the Bers slice of a punctured torus groups, which, anyway, I won't define it if you haven't seen it, but if you look, there's these very beautiful computer pictures of it, but if you look at them, they suggest that the Hausdorff dimension probably isn't 2, but somewhere strictly between 1 and 2. So, I don't know if I want to. Okay, so this is a problem that's fascinated me for a long time, but I've never really had any idea how to attack it. Okay, so there's sort of a lot of stuff still to understand in Bumpanomics. In general, these pictures suggest that there's sort of some very fractal nature to the boundary from a geometric viewpoint, but we really don't have any results of that kind, and we don't really understand how this bumping happens. What sort of bumping can occur when the fundamental group is freely decomposable. Okay, so I promised you a cool argument. Take a respite from Bumpanomics. So this came up in Dave's talk, and I also alluded to in mine. Thurston showed that if you start with a convex co-compact manifold with non-empty conformal boundary, any cover of it with finely generated fundamental group is topologically tame. And as Dave mentioned, that this is a topological result. It was far beyond what could be done with purely topological techniques, and it's a very simple application of all-force fineness theorem. So let's just do it. So if you have a cover, then you have a finely generated subgroup, gamma naught. Now, since your manifold is convex co-compact, it has its convex core is compact, so it has finite diameter, d. So every point is within d of the boundary. Lift that up to the universal cover. Well, the cover of the convex core is just the convex hull of the limit set. Every point of the convex hull of the limit set is within d of the boundary. Okay, now pass to a subgroup. The limit set of the subgroup is contained in the limit set of the big group, so the convex hull of the limit set of the subgroup is contained in the convex hull of the limit set of the big group. So if you start inside the convex hull of the limit set of the subgroup, and you can get outside the bigger convex hull in time d, you can certainly get outside the smaller convex hull in time d. So the distance to the boundary is less than d. And when you project downstairs, that means the distance from x to the boundary of the convex core is less than d. But all-force fineness theorem tells you the boundary of the convex core is some finite collection of closed surfaces. Well, so now you're within distance d of a compact set and you're closed, therefore you're compact. Therefore, n naught is convex co-compact. That's the whole proof. So there's a huge hammer here, which is all-force fineness theorem, but otherwise it's a very simple argument. And now if you hit it with another huge hammer, which is Thurston's geometrization theorem, you get a purely topological statement. So you can start with a compact irreducible H-roidal manifold with empty, non-empty, non-empty boundary, and you pass to any cover with finite fundamental group, that cover is topologically tame. And I think at the time he did this, you know, they could maybe do Z, and maybe sometimes Z plus Z, and maybe they could handle the boundary subgroup, but it was sort of hard work. And this is, if you know all force fineness theorem, well, and, you know, versus generalization theorem. Okay. 15 minutes. So you're going to get 15 minutes of dynamics on character varieties, just so I can talk about something that happened in the last few years. So there's another natural dynamical system sitting in the background here, which is you can look at the outer automorphism group of your three-manifold group, which is just automorphisms up to conjugation. So we don't care about conjugation by some group element. This acts naturally on the full character variety. And you just do that by precomposing by the, it works better if you precompose by the inverse of the automorphism. Okay, so that's the natural action on the character variety. And you can ask yourself, well, what are the dynamics of that? And one set which is preserved by this action is AH of M. So you might ask yourself, well, is it properly discontinuous on AH? What could you say? Well, one thing you can say pretty quickly, using all the stuff we just did, is that if you have a component in the interior, and its marked homeomorphism type is M prime H prime, then the stabilizer of that component is just identified with a subgroup of the mapping class group of the boundary. Okay? Well, the mapping class group of the boundary acts properly discontinuously on type-inner space, therefore, out pi 1M acts properly discontinuing on the interior. So, very quickly, using the classical deformation theory of Kleinian groups, you see that this group action is properly discontinuously on the set of convex co-compact representations. And well, there's a lot of questions you might ask, but one question you might ask, is this the biggest domain discontinuity you could have? Or is there something bigger?
Stop reading this.
Too much notation?
No, it's just a subgroup of distinguished. Is that a quotient group?
Yeah, the twist group is a normal subgroup.
Oh, you know what that group is.
Yeah, right, yeah. Really, let's just think, or I should have probably just said incompressible boundary, then that would be a trivial group, it would be much.
Okay, it is basically identified.
Yeah. Yeah.
Not abstract.
Right. Oh, wait a second.
It's not normal. Surface almost is
Yeah, you're right, it's normal in mod M, but it's not normal in the full mapping class group, I think.
Yeah.
That's right, that's a good point. Yeah, let's suppose and this is fine, but let's just suppose for the point where we're saying that, doing here that M has really indecomposable fundamental groups, or mod not M prime is trivial. And then you just identify the stabilizers or see the subgroup of the mapping class group of the boundary, which is what I said out loud. The problem with doing these electronic slides, you start getting you sort of feel like you have to state it instead of the simple thing. You have so much room, you can just state the whole thing. Okay. So you identify with the subgroup of the mapping class group, and because the mapping class group acts properly discontinuously, out acts properly discontinuously. So, you know, there's these stabilizers which are associated with the mapping class group of the three manifolds sitting within there, and then these exotic homotopy equivalences permute the components around. So don't affect the proper discontinuity of the action. Okay, so there's two extreme cases. Well, first of all, Johansson showed that if your group is acylindrical, then the outer automorphism group is finite. And that's an if and only if condition. Because once you have one of these interesting annuli, you can Dane twist about the annuli, and you get an infinite order automorphism. So in particular, well, if the group's finite, it acts properly discontinuously. That's one extreme. It acts properly discontinuously on anything it acts on. So in particular on the character variety. So that's one not so interesting extreme. The other extreme is sort of in this state of just a conjecture at the moment. Is in the case when you have a surface cross I. So that's the most cylindrical manifold of all cylindrical manifolds. It is made up of cylinders. And the interior is quasi-Fuchsian space. And out pi 1f is essentially the mapping class group up to index 2. And what Goldman conjectures is that quasi-Fuchsian space is in fact the maximal domain discontinuity in this situation. And moreover, on the complement, the action is ergodic. So that there's this very nice dichotomy in the dynamics. So property is continuous on one set, ergodic on the complement. It's sort of a nice picture. But the only piece of evidence, or the best...
You're assuming it's at cross I?
Yeah.
And then was there ergodic on something and properties continuous on something else?
It's properly discontinuous on quasi-Fuchsian space, and then and the conjecture is that it acts ergodically on the complement of quasi-Fuchsian space in the space of all representations of surface groups, the character variety. Yeah. Yeah. And one thing you can show, and this was sort of an argument, I don't know who all knew this, but Yair knew this, and my student Michelle Lee wrote it down in a paper because she needed it, so I put her name there too, is that every point in the boundary of quasi-Fuchsian space is a limit of fixed points of infinite order elements of the mapping class group. So in particular, points in the boundary of quasi-Fuchsian space can't possibly be the domain discontinuity. So if you're going to enlarge the domain discontinuity, it's going to have to be by adding something way away from quasi-Fuchsian space. So that's sort of convincing. I mean, this proof uses the density of cusps in the boundary of quasi-Fuchsian space.
So if you have two things that come, one of these points, two components.
Right. So it turns out whenever you have a primitive essential annulus, you can use a relative of the bumping, sort of a simple relative of the bumping construction to show that the action is not properly discontinuous on AH. So you can use that to construct points where the action can't be properly discontinuous. Okay. But it turns out that I think one's nature when doing a kind of group is to assume that the surface, once you've done the surface group case, this is how the ELC went and how density went. You do the surface group case and everything else is sort of like the surface group case. This is what we're used to. But it turns out the surface group case is actually quite anomalous here, or at least conjecturally anomalous, because every other case we studied, you can enlarge the domain discontinuity. So I think the first result of this type was due to Yair to show he looked at the case of the handle body. And in this case, you're looking at the outer automorphism of the free group, and he made a bigger set where the action is properly continuous. This is the set of primitive stable representations, and then along with Gelander, he produced another set called the redundant representations where the action is ergodic, and then you might hope that the difference has measure 0, but what's your guess today, Edgar? Tomorrow, yes, okay. And then with Pete Storm, we studied the case where the fundamental group is freely decomposable, but you're not an interval bundle. And here the techniques are very much characteristic submanifold techniques, so they're sort of necessarily quite different, and you can show that you can always make the domain discontinuity bigger. And then Michelle Lee, in the twisted interval bundle case, came and showed that you can make the domain discontinuity bigger there. And why is that surprising? Because remember, the fundamental group of a twisted interval bundle is just a non-orientable surface. So this says that the actions of the mapping class group on the character variety of a non-orientable surface is already very different than the action on the character variety of an orientable surface group. So this is, at least when you're first thinking of it, perhaps something of a surprise. And then you might ask yourself well, I can make the domain of discontinuity bigger. Can I ever just make a domain of discontinuity which contains all the discrete faithful representations? And it turns out sometimes you can. And you can do so exactly when your manifold contains no primitive essential annuli. So if you have a primitive essential annulus, you can do some sort of trickery to show the failure of proper discontinuity. Or actually, you can use this trick of Yair's to show that you can also use this trick of Yair's to show that you're a limit of fixed points. So it would even be an easier thing to do. But if you don't have any primitive essential annuli, your outer automorphism group can still be infinite, but you can act properly discontinuously on some open neighborhood of a set of discrete vector representations. So here's an example of such a manifold. You might think,
This is all in the non-injective case, right?
what?
This is all in the non-injective case, without the effective case.
No, this is true. This is true in general. Yeah. Actually, it turns out if you have I'm actually assuming there's no tori in the boundary. Is what I am assuming. That's in the background. But once you have a compressing disk, you can make an essential annulus from it. So it turns out that once you have a compressing disk, you have an essential annulus, and so everything goes away. So it's really the incompressible case that's hard here. So how would you make such a manifold? Sort of similar picture. You would take one of these annuli going twice around, like so. So picking that picture up. And I'm going to take 3 copies of that and glue 3 different acylindrical manifolds to each of them. So the first annulus, you do 1 acylindrical manifold, 2 along an annulus in its boundary. Second, you do the same. Third, you do the same. Then it turns out that if you do this, that the mapping class group is exactly Z2. Well, sorry, is up to finite index Z2. And it's generated.
Glue them on the parallel copies.
What?
Glue them on the parallel.
Yeah, on parallel copies, this guy. And it turns out that there's a finite index subgroup of the mapping class group generated by Dane twists about those non-primitive essential annuli. So, and in fact, in all these cases, the fundamental group will be this outer automorphism group will be virtually abelian.
So the dynamics of these elements of that
Right. Yeah, I don't know.
I'm sorry, that was
Yeah. Okay. So I was going to say something about the proof, but I think I would just stop since we're about out of time.
Questions?
So I was going to say again that I think this is sort of a cute idea. But so how are you going to show the proper discontinuity? Well, what you're going to do is I'm going to find a free subgroup of the fundamental group of this 3 manifold, which is preserved by the outer automorphism group. And once I've done that, if I can find a free subgroup, if I know that that free subgroup is a Schottky group, that's an open condition. And so if I can ever find a free subgroup which is preserved by the mapping class, preserved by the outer automorphism group, such that the outer automorphism group injects into out Fn, then I can find some open neighborhood of the representation of the free group on which the action is properly discontinuous. That's going to pull back and give some neighborhood of the representation of the full group on which the outer automorphism group is properly discontinuous. And so what you do is you just take a group generated by the core curve here, and then you run one curve out into each acylindrical manifold you've added. So you can make a free group that way, and by ping pong, what? Four generators here, and by ping pong, generically that group's Schottky. So if you take any discrete faithful representation, generically the group you get is going to be Schottky. And in fact, I think I haven't written this down carefully. I think what this shows is the domain of discontinuity in this case for the action on the full characterized as full measure, because this is a generic condition that these groups, that one of these groups is shot. So that's the idea.
So how much discount did you get? How much domain discount?
Well, I think what all you need to know is I call these groups registering subgroups. So all you need to know is once you know that you can find some registering subgroup of your three manifold, if its image is Schottky, you win. But there's, then you're in the domain discontinuity for this group action. So so there's the domain I defined is you take the set of all representations that some registering subgroup is Schottky. And the action of our homeomorphism on that is properties continuous. I'm pretty sure that is full measure, but I haven't really checked it carefully in this case.